So we have shown that if x star is a local minimizer for the problem of minimizing f of x over the constraint set x, capital here, then this product is greater than or equal to 0 for any feasible direction d. And feasible direction is considered with respect to the set, which is x, and the point x star. So we are looking at an arbitrary feasible direction at the point x star, and the gradient of f at x star multiplied by any feasible direction at that point is greater than or equal to 0. So let's try to understand this result a little better, and let's consider different cases here, okay? So let's say this is our set x. So we are illustrating things on an example with two variables so that we can illustrate things on a plane. And consider the case when x star is some interior point. So what is an interior point? This is a point that belongs to the set together with some ball around it. So there is some small radius ball around x star such that this ball is completely within the set x. And it's obvious that for an interior point, any direction is feasible. So whatever direction you look at, you are still within the feasible region locally, right? And feasible direction is a local concept, okay? So we are concerned with being feasible in some small neighborhood of a point x star. Of course, local optimality is also a local property of the point, so this is what we focus on, the small neighborhood around the point x star. So now, because for an interior point, every direction is feasible, if I take some arbitrary direction d, so this is for any d in Rn, and of course, again, the illustration is for the case when n is equal to 2, then the gradient of f in x star transpose times d is greater than or equal to 0. So this is the optimality condition, the necessary optimality condition that a point x star must satisfy if it is a local minimizer for our problem. So now, because every direction is feasible, I can write the same condition for the direction minus d. So if I use minus d instead of d, then I'll have the gradient of f in x star transpose times minus d is greater than or equal to 0, which is the same as saying that the gradient of f in x star transposed times d is actually less than or equal to 0. So if I look at these two inequalities here, both of these together are equivalent to stating that the gradient of f in x star transpose times d is in fact equal to 0. And this must be the case for every feasible direction d, and because every direction is feasible for an interior point, this must hold for any direction d. So in particular, I can take the direction d, which is given by the following vector. Say I have the first component equal to 1, and the rest components are equal to 0. If I take the vector d in this form, then I'll have the gradient of f in x star transpose times this vector is equal to 0, which means that the first component of the vector of the gradient, which is df x star over dx1, is equal to 0. All right. So similarly, if I take vector d where the second component is equal to 1 and the rest components are zeros, I can show that df in x star over dx2, which is the second component of the gradient vector, is also 0, and so on. We can show that all the components of the vector of the gradient are in fact zeros. So therefore, we have the gradient of f in x star must be equal to 0 in this case. Now, this looks like something that we have seen before for one-dimensional problems. So this is the same as saying that if a point is a local minimizer, then the derivative of f in this point must be equal to 0. So now this is for an interior point. All right, so this is the property of an interior point, and because every direction is feasible at the interior point, we have this corollary here, so that if x star is a point of local minimum and x star is an interior point of the set X, then the gradient of f at x star must be equal to 0. This is the first order necessary condition that we'll use quite often. In particular, if we talk about an unconstrained minimization problem, so if I look at the problem of minimizing f of x, where x is in Rn, so in other words, this set x capital is given by Rn. For this case, every point of Rn is an interior point. Therefore, if x star is a local minimizer for our problem, so this is called unconstrained minimization, then the gradient of f in x star is 0. This is what we call the first order necessary condition for a local minimum. Quite often we'll use the abbreviation FONC. This is a necessary condition, but it's not a sufficient condition for a local minimizer. So what's the difference between a necessary condition and a sufficient condition? A necessary condition is a condition that must be satisfied assuming that a point is a local minimizer. Whereas a sufficient condition is something such that if it is satisfied, then the point is a local minimizer. All right, so let's consider an example which shows that this first order necessary condition is not sufficient. So let's say consider the problem of minimizing f of x equal to x cubed. So we're talking about a one-dimensional problem. The plot for this function will look like this. If we take the gradient, in this case this is just the first order derivative, f prime of x is 3 times x squared, and if we make it equal to 0, then the only solution we have is x equal to 0. Alright, so 0 point is the only candidate point for a local minimizer here, and of course it's easy to see that x equal to 0 is not a minimizer or maximizer for our problem. Therefore, we can see that even though the property is satisfied, the first order necessary condition is satisfied, obviously the point is not a minimizer. This is not surprising, this is just a necessary condition, but the condition is not sufficient, as we can see from this example. In fact, you could have a minimizer that satisfies this condition, you could have a maximizer that satisfies this condition, and you could have a point like this, a saddle point, as we call it, so that also satisfies this condition, but it's not a minimizer or a maximizer. All right. Another thing we can see in this example is that even though we have a point that satisfies the first order necessary condition, we don't have any minimizer or maximizer for this problem at all. Therefore, the question of existence arises. In other words, how do we know whether a minimizer even exists for our problem? We'll come back to this question and we'll discuss applications of first order necessary condition a little later. But first, I wanted to go over the case when actually x star is not an interior point of the feasible region. When the point is the interior point, we saw that our optimality condition reduces to just checking whether the gradient is equal to 0. All right, so but if we have a point that's on the boundary, so let's say if our x star was here, then the direction d that we have in the optimality condition, which says that the gradient f of x star transpose times d must be greater than or equal to 0, the direction d becomes important. Okay, so because not every direction will be feasible anymore. So for example, a direction like this is feasible, but a direction like this is not feasible. So let's see what exactly this product here means. How can we describe it in words also? It appears that this product is in fact nothing else but the directional derivative of the function f at the point x star in the direction d, so which we'll define next. Let's look at a direction d. Say, what do we do if we want to characterize the rate of increase of the function f at x star in the direction d. We look at the rate of change of the function, right? So the rate of change of the function would be f of x star plus alpha d, where d is this direction we are looking at, and then as before, we can assume that the length of the direction d is 1, so we normalize it. If we do that, then alpha measures exactly the step size that we take from x star in the direction d. Anyway, so if I take step size alpha in the direction d from the point x star, so this will give me the new value for f. If I subtract the previous value of f, which is f of x star, and then divide by the length of the step that I'm taking, alpha, then this is exactly what we call the rate of change of function in the direction d. If I want to get the rate of increase of f at the point x star, I need to take the limit for alpha tending to 0 from the positive side, and then this will give me what we call the rate of increase of f at x star in the direction d. This is also called the directional derivative of f in the direction d. In fact, when we assume that the length of vector d is equal to 1, we call it the rate of increase. But for an arbitrary d, we call it the directional derivative of f at x star in the direction d, which is also denoted by df in x star over dd. The directional derivative is, of course, a scalar. If we look at the vector of the gradient, which we denoted by nabla f of x star, it consists of essentially a bunch of directional derivatives. If I look at the first component, then what is this exactly? This is nothing else but the directional derivative of f in x star in the direction d e1, where e1 is the vector which has the first component of 1 and the rest are zeros. So this is a particular set of directional derivatives that we use to form the gradient vector. Alright, so but for an arbitrary direction we can define the directional derivative like this, and in fact we can show that what we have here in the product is nothing else but this directional derivative that we just defined. So how do we do this? So we'll denote this function, considering it as a function of alpha only, we'll denote it by phi of alpha, for example. So if your phi of alpha is given by this expression here, then by setting alpha equal to 0, I'll get exactly f of x star. Right? So phi of 0 then becomes f of x star. So then this is phi of 0. And essentially what I have here is the limit of phi of alpha minus phi of 0 divided by alpha when alpha tends to 0. By definition of the derivative of this function phi, this will be phi prime of 0, so the derivative of this function phi at the point 0. On the other hand, I can use the chain rule to compute this derivative alternatively. Alright, so let me explain what I'm talking about here. So we are talking about the function phi of alpha, which is given by f of x star plus alpha d. So this is the function of alpha, which I can represent as follows. Let me denote the argument of f here by, say, g of alpha. Okay, so then g of alpha is just x star plus alpha times d. So this function is linear with respect to alpha. So then this will be like f of g of alpha. So if I want to take the derivative of phi of alpha now, I can use the chain rule, and this will be the product of the derivative of f first multiplied by the derivative of g with respect to alpha, right? So, and in particular, if I have this derivative phi prime of 0, it will be given by, first we take the derivative of the external function, which is f. So we have the gradient of f in this point here of g of alpha, where alpha is equal to 0. So, and when alpha is equal to 0, the argument will be equal to exactly x star, right? So, and then we need to multiply this by the derivative of g with respect to alpha at the point 0. So, and the derivative of g, because our g of alpha is just x star plus alpha d, the derivative of this with respect to alpha will be just the vector d. So we see that this phi prime of 0 is exactly the product that we had in the optimality condition. This is the same as the directional derivative, because we see this connection here, so this is exactly the same thing, right? Therefore, this optimality condition that we have here, what it essentially says is that the directional derivative of f at x star in any feasible direction d is non-negative. In other words, the rate of increase of the function f at x star in any feasible direction is greater than or equal to 0. So which means that if you are talking about the rate of increase of the function, we say it has the positive rate of increase, it means that the function is essentially increasing. So then what optimality condition says, if we translate it to the simple language, this condition tells us that if x star is a local minimizer, then the function is not decreasing in any feasible direction, right? So because the rate of increase in any feasible direction is non-negative. So this is essentially the meaning of this optimality condition. All right, so as we have already mentioned, this first order necessary condition is not a sufficient condition and it doesn't guarantee anything. We only know that this condition is satisfied if the point is a local minimizer. Okay, so but in some cases this condition can actually be very helpful, in particular if, for example, we know that the global minimizer exists for our function, then we can find the minimizer by checking all the points that satisfy the first order conditions, right? We know that if a point is a minimizer, then it must satisfy the first order necessary condition, right? So now that we know that the minimizer exists, the minimizer must be among the points that satisfy the first order necessary condition. Therefore, we can just take the points that satisfy the first order necessary condition and then evaluate our function in each of these points and pick the best point, and this point then must be the point of a global minimizer. All right, so but this is assuming that the minimizer exists. How do we know when the minimizer exists? So this is actually a very non-trivial question. So this is an extremely difficult question, but in some cases we can actually check that the problem satisfies certain conditions which guarantee you that the problem will have a minimizer.